recording. Good morning. Last day I left you with a little something to think about, right? What if we had to find the probability? Hey, what are we talking about here? Remember we were talking about the binomial distribution. And so maybe, just maybe, I'll bump this down a little bit and do a quick review. Right, we said, let me see if I can bump that down. So what we said was, just for some review, we talked about the binomial distribution, which happens when we have outcomes, so there are only two possible outcomes. And we said, well, we can reduce a lot of situations to two possible outcomes. And that's what makes the binomial distribution so useful, right? And so binomial distribution has two possible outcomes. Such as success, failure. Okay. And the probability of k successes in n trials. Oh, looks like I'm going to need to make even more room here. The probability of k successes in n trials, right? So if we're shooting hoops or if we are looking at stock prices, we're assuming that they increase or decrease independently of each other. So that's something we're going to talk a little bit more about today, is that we are assuming that things are independent, and that's not necessarily the case, right? Especially with stocks, we understand that. But we're assuming that for this example. So in n trials means that we're trying to see a success n times, but of course we're only going to see k, some number k successes. So the probability of k successes in n trials is the probability that x equals k, which is n choose k, so we had to use that choose function, right, times p to the power of k, right? P is the probability of success, okay? And k is the number of successes. So of course we have to have some probability of success. K is the number of successes, and then 1 minus p, or I usually tend to gravitate towards just calling it q, right? But here I'll write 1 minus p to the n minus k, right? Yn minus k. Well, in n trials, I have k successes. So how many failures do I have? I must have n minus k failures, right? With a probability of 1 minus p. Okay. So from here, what we can do is we can consider some number of trials, and we can find exact probabilities. So notice that these are exact probabilities. But what we saw was, I think we saw the probability of more than 3, not including 3 successes. So if we have 5 trials, which we're considering in this example, right, from last day, if we are looking at 5 trials, then more than 3, not including 3, would be 4 or 5, right? So as soon as you're saying or, you're going to have to add to those probabilities. My voice needs to wake up. I'm here, but my voice is catching up. So here, right, we can find the probability that x equals 4, and then we can find the probability that x equals 5, and then we can add those up, and then we have our probabilities, right? So then I left you with the problem, kind of a thinking problem. So what if we have to find the probability that there's at least 1 increase in the 5 weeks, okay? And so, and I have a little reminder here that n is 5. We're looking at 5 weeks. The probability of an increase each week is 0.56. Okay, so because that's the probability of an increase, then the number of successes have to be the increase, right? And so these successes and the probability of a success, they have to match, right? And there's a sneaky problem, and I can't remember if I used it or if I want to use it or not. But anyways, I have one that I like to show sometimes. And you're given the probability of a success, but then what if I asked you, what's the probability that it'll decrease or stay the same for 3 weeks, right? So that would be K failures. So then you would have to convert your P to the probability of essentially a failure in this situation. But you can do that. You can move back and forth. So you have to define your success, and then the P has to attach to that success, right? And so in this case, right, I find it helpful if we list the possible outcomes, right? And so we said before, we said that X can be 0, right? You don't want to forget about 0 increases. That's the one that people tend to forget, and it really messes things up, but it is an option. So you kind of want to have that stopper and say it, no, 0 is an option. 0, 1, 2, 3, 4, 5. So what could I do if I want to find the probability that there's at least one increase in 5 weeks? Well, at least one increase would be 1, 2, 3, 4, 5, right? So it would be everything except for 0. You could, right? We could find the probability that X equals 1 plus the probability that X equals 2 plus the probability that X equals 3 plus the probability that X equals 4 plus the probability that X equals 5. But that feels like a lot of work, right? And so we don't actually need to do that. A lot of the stuff that we learn, it's just because we get lazy. We don't want to do these calculations. Isn't there a better way to do this? There is, right? We've listed all the possible outcomes. And so the total probabilities have to add to 1, right? That's a fact of probabilities. Okay. And so here, purple, why not? Since we have listed, oh, weird. Since we have listed all possible outcomes, the total probability, the total probability must be 1. Okay, so we could, and I am emphasizing could, right? We could find the probability of that X is at least 1. So if I'm going to introduce some inequalities here, find the probability that there's at least 1 increase. X is greater than or equal to 1, right? That's at least 1 increase. Well, that's the probability that X equals 1 plus the probability that X equals 2 plus the probability that X equals 3 plus the probability that X equals 4. And I'm going to give myself a little bit more room here. Plus the probability that X equals 5. This wouldn't be that much work. We've already found the probability that X equals 4 and X equals 5. So it's not, insane to go ahead and find these other 3 probabilities, but we get lazy, right? And so what we could do is we take the complement of this essentially, right? And so we could find this, or say that the probability that X is greater than or equal to 1 must just be 1 minus the probability that X equals 0, right? Because the total of these probabilities have to add to 1, right? So then if I just chop away the one option that I don't want, well, that's going to leave me with the remainder here, right? And so that's a trick that you're going to want to leverage. And it takes some practice, but usually as soon as you see things like at least some number, right, that should get you thinking, okay, maybe there's a shortcut here that I could use. It might even be, at least 2 increases, right? So then it would be 2, 3, 4, 5. So then you could, I think of it as chopping off. Then you could chop off 0 and 1, right? So then in that case, and I'm going to remove this after because it doesn't apply to this situation, but then I could go making sure that you chop that off as one value, right? Or minus again, it's fine. But so you've got options, and kind of the trick with these problems is the more of them that you see, the quicker you'll be at kind of, okay, I know a shortcut here that I can use, right? And so this is kind of the most common one. It's where you look at all the total probability and say, oh, I actually don't want to do all these calculations. No, thank you. I want to use a shortcut. Okay. Good. So did I ask you to do anything else? I think that was it from last day. Let me just confirm. Okay. Good. So we did talk about the binomial distribution will have a mean and a standard deviation, and we said what they were, right? And we're going to use them again. So now I'll call this kind of the end of our review here, even though that wasn't review, but it was kind of filling us in from last day. So one cool thing is, well, one scary thing, I should say, let's start there with the scary thing, is what if I was looking at 52 weeks, right? There's 52 weeks in a year, right? So we're just looking at 1 year. And so if we're considering this example here, what if I wanted to talk about the number of increases in 52 weeks, right? Over a year. Well, so now, what if I wanted to find what's the probability of 34 or more increases, right? So here, what if we wanted to consider all 52 weeks of the year? What if we had to find the probability of at least 34 increases? Ugh. What if we had to find the probability of at least 34 increases? Okay. We could do that, right? N would be 52 in this case, right? So N would be 52, P would still be 0.56, and we want to find the probability of at least 34 increases. So the probability that X is greater than or equal to 34, okay, that would be 34, 35, 36, 37, 38, 39, all the way up to 52, right? Even if I did the 1 minus trick, I would still have to do 1 minus the probability of 0, 2, not 1, no, 1's included, 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 33. There's really no easy way to do that, right? And so what we would have to do is we would have to find the probability that X equals 34 plus the probability that X equals 35, all the way up to the probability that x equals 52, right? That feels like the least number of calculations. That's still too many, right? Too many for me. I don't want to do that. We have software now, so it's easy enough. We could brute force it, right? But we don't want to do that, and we don't need to do that, right? So what happens is a really cool thing happens if our sample set, or if the number of trials rather, n is a sample size, which is the number of trials. If the number of trials is large enough, then we can apply what we call the normal approximation to the binomial. So here, if n is large enough, we can apply the normal approximation to the binomial. Okay. So that's a really cool thing. That's going to save us a lot of work. How does it, how can we use it? And what is large enough, right? That's the problem. We say if n is large enough, we need to have some guideline, right? What makes it large enough? Okay, and so that's where we're going to start here. And let's see here. So the normal approximation to the binomial, I'll grab this whole blurb here. Oh, hey. So when the number of possible outcomes is larger, the large number of trials, really, right? So if n is large enough, we can use a normal approximation to calculate the binomial probabilities. What we're going to use is we're going to use mu equals n times p, and sigma is the root of npq. We saw those last day, right? We said, okay, if you want a mean and a standard deviation for this thing, this is what you can use, okay? And what we're going to do is we're going to be able to calculate a z-score, right? That brings us back to the normal distribution, which we worked on first thing in this chapter. Can't remember when it was. I feel like it was last week. It was, because we did an example on the Friday. Yeah, okay, it's all coming back. So we can find the z-score calculation if we have a mu and we have a sigma. We just need an observation, right? And so, and then to find probabilities, that's an area under the curve now, right? For the normal approximation or for the normal distribution, probabilities are areas under the curve, right? So here, the first thing we need to do, though, we can't just go ahead and use it willy-nilly. We have to make sure that n is large enough, okay? So we can use the normal approximation to the binomial as long as we expect at least 10 successes and 10 failures, okay? And so what that means is we have to have n times p is the expected number of successes. Expected number of successes, right? Thinking back to the simplest scenario, if I flip a coin 100 times, how many tails am I expecting to see? I would expect to see roughly 50. How did I get to 50? Well, I did 100 times 0.5, right? The probability of a tail is 0.5. Same thing. How did I find the probability of a failure if a success is tails? Well, then I would have to take 100 times 50 or 0.5 to get 50, right? And so even if we switch P to something else like 0.56 and Q would be 0.44, right? Then we can still calculate it the same way, right? And so N times P is the expected number of successes, and n times q, remember where q is 1 minus p. So here, recall Q is 1 minus P. So NQ is the expected number of failures. Okay. What does that mean? If we're forcing at least 10 successes and 10 failures, well, my total number of trials can't be less than 20 then, right? Because I need to have at least, or I need to expect at least 10 successes and 10 failures, okay? And so what happens is that's maximized, right? Or I guess the total number of trials is 20, so minimized, I should say, if P is 0.5 and Q is 0.5, right? In this case, we have something a little bit different, so we're gonna need a slightly larger sample size than 20, right? Or slightly more number of trials than 20, okay? And so in this situation, right, if we were to look at the 52 weeks, I have a different example that I want to get into because it gets hard when I use the same example over and over, right? But if we think about the 52 weeks, 52 times 0.56 is what? 52 times 0.56 is 29.12, right? And so here, if we were to calculate probabilities from all 52 weeks, could we use the normal approximation? Right? Just starting with one that we know, right? So here, N times P is 52 times 0.56, which is 29.12. That is more than 10. So I'm expecting more than 10 successes. That's great. In fact, I'm expecting 29.12 successes or increases. So usually what I do is I show that that's greater than 10, and I like to have a little check mark here. That's just for fun. And it's, I don't know, oddly satisfying to see a green check mark, right? So what if we try N times Q? Well, N times Q is 52 times 0.44. which 52 times 0.44 puts me at 22.88, which is also more than 10. So it checks out, right? So yes, we could use the normal approximation to the binomial, right? Okay. Yes. We could use the normal approximation. Okay, so that's how you're going to do it, right? And so here, if you add these up, that's going to add to 52, right? Because I'm just multiplying 52 by 0.56 and 0.44, so that should add to 52, right? And so you're just splitting your the number of trials into expected number of successes and expected number of failures. You don't need to round or anything. All we're doing is we need to make sure that it's more than 10. Okay. Usually if I get you to use the normal approximation, of course, in this course, it's always going to check out. It's just, you need to show me that you remember to check it. In real life, right? I'm not here to tell you what to do in real life. So then, of course, it has to be something that we're checking, right? Can I do this? Can I use the normal approximation? Right? And it's not that bad. It's just an extra step before you go ahead and use it. So I've got an example that I want to use. suppose that the Canadian Blood Services anticipates the need for at least 1,850 units of O negative blood for a particular region this year. It estimates that it will collect blood from 32,000 donors, and only about 6% of people have O negative blood. This is a very real world thing, right? We know this, right? And so the only thing that they're estimating the need, so that would be its own calculation, right? But here we have that need, and they're estimating how many donors are going to come through the door, right? But and then it's established, we know what percentage of people have which type of blood generally. So it is based on estimates. But of course, we're assuming that these are educated estimates. So in this case, what is a success? A success in this case is going to be if one of these 32,000 donors comes in with O negative blood, right? And so a success is having O negative blood. A donor has O negative blood. Okay. What are N and P, right? Well, first, let's take a step back. Is this a binomial situation or not? Right, I kind of jumped into it. It is, right? Because a person either has O negative blood or they don't, right? I don't. Bummer. I'm not one of the 6%. But if you are, then that's great, right? Then you've got this fancy blood that everyone wants. And so my useless blood, it's just for me. Right? And so here, this is a binomial situation because you either have an O negative or you don't, right? We've reduced it to, we know that there are other blood types, right? And we could consider those. But in this case, everyone who's not O negative is lumped into the failure situation, right? And so it is a binomial situation. And we assume that all of these donors are independent of each other, right? I'm going to talk more about that independence today later, but for now, right, we just assume that all these donors are independent of each other. It's not necessarily the case, right? Usually if your sister is donating blood, you go with her, right? And you're more likely to have the same type of blood, but for now, we just assume that everyone's independent, right? N and P in this case. So how many times am I trying to get O negative blood? We're assuming it's going to be 32,000 times, okay? And so here, N is 32,000, right? The probability of a success for each one of those 32,000, well, that's going to be 0.06. Remember, we usually report probabilities as percentages, but whenever we're doing math, right, we need to convert it to a decimal, right? So that's important. What's the mean and the standard deviation of the distribution? Well, now I'm going to need a little bit more room, I think. In fact, maybe I'll do this. There. I'll bring in the rest later. So the mean is N times P. Nice. Which we established last day. So that's going to be 32,000 times 0.06, which, right, don't get bogged down. If I asked you, okay, if the probability of someone walking in with O negative blood is 0.06, how many would I expect out of 32,000? You would just do that calculation in your head. Well, not in your head, but you would know to do that calculation, right? 32,000 times 0.06. So that's exactly what we're doing here, right? And so I'll do it on here. Alex is on it in the chat, but I'll just do it here, times 0.06, 1920. Alex is awake. How about the standard deviation? Yeah. Well, it's only because one time I actually did, it was a long time ago now, but I actually did use the number in the chat and it turns out it was wrong. So, and it messed up everything. So now but I screw up. So it's good to verify exactly. Okay, so sigma is going to be what? The square root of NPQ. This is one of those things that you probably want to have on your formula sheet. In fact, unless you can remember it, right? I'm just going to look at our formula sheet that I don't have here, it looks like, but I did post it. Do I have it anywhere? Maybe not. Huh. I did post this formula sheet, right? You've got the binomial distribution, and then we have the mean and the standard deviation on here, and where Q is 1 minus P. So, sigma is going to be the square root of 32,000 times 0.06 times Q, which is 1 minus 0.06, which puts me at 0.94, right? And I say that because I need to confirm because I don't trust myself. Yeah, good. That's one of the problems with doing, because I did my undergrad in math, right? And so by the end of my undergrad, I was doing things like 1 + 1 on my calculator because I had to be sure. And so, so it gets really weird because everyone thinks that you're so confident, but really all it does, getting a degree in math, is it just makes you less confident in your basic math abilities. Yeah, so here, so if I go ahead and I multiply that through, I'm going to be taking, and I'm showing the square root here, 1804.8. It's really important, and a lot of people tend to forget that square root, but you don't want to forget that. If you forget that, that's the variance, right? And so we need the standard deviation, and so the square root of that is approximately, so I'll do a squiggly equals 42.48293775. Okay. So you could round it. I would keep at least 3 or 4 decimal places. Ideally keep all of them, but sometimes it gets a little bit nasty. So the thing is, these, you know, online quizzes, so whether it be a Moodle quiz or, you know, anything, they're going to be keeping all the decimal places. So the more that you can keep, the better it is. Okay, but I do go through and I check all the answers, and if, you know, if there is like a tiny discrepancy and it's not because of an error, then I do give you the marks after the fact. Okay, so I do go through and do that, but you're safer if you just keep all your decimal places, because that's what the brain behind the scenes is doing, right? And so the more you can keep, the better it is. Unless I say that you can round it, then it's safe to round it. Okay, so if I've told you that you can round a value, then you can use the rounded value. So if I tell you to round to 2 decimal places and you end up having to use that value later on, you can use the rounded value. So it's kind of like a weird situation. Okay, and if you're unsure, then just ask me. Okay. Okay, so we have the mean, we have the standard deviation. Great. Let me see if I can set this up here. What? Hey, doesn't want to let me do it. Set up the formula. There's a reason I ask you to do that, for getting exactly 1,850 units of O negative blood from 32,000 donors. Okay. So what we're trying to find here is we're trying to solve the probability that X equals 1,850. Exactly, right? So that's when X is equal to. So if we think about do you have the formula memorized already? Maybe what I should do is I should bump this down just one line and do a little reminder that the probability that X equals K is N choose K, P to the K, Q to the N minus K. Okay, so in this case, right, it's going to be the probability that X equals 1850 is 32,000 choose 1850. So imagine you're looking at 32,000 trials, and your calculator is not going to be able to do it. That's why I said set up the formula, but we're not going to be able to get a number unless we use some heavy computing. I'm not even sure Desmos is going to do it. I'll try it with Desmos to see if we can get a number, but I suspect not, right? Because what we're asking it to do is make a tree diagram with 32,000 layers, and then exactly how many times can I get 1,850 successes? Okay, so let's just see if we can do just this part of the calculation. I'll check in Desmos. I suspect I can't. Clear all. How did I use that function? I think it was in the functions, NCR, and then I go back here, 32,000, comma, 1,850. It's undefined because it just can't do it. There's too many options. You'd have to use, I think, something like probably Maple could maybe handle it, but it doesn't want to do it. And that's okay. We don't need it to, right? So that's why I said set up the formula that you would use, right? And so here, P is 0.06 to the power of, I want to have 1850 successes, which means 0.94 to the power of 32,000 minus 1850 is, then I would want 30,150 failures. Okay. This is too large for a calculator to calculate. All right. 0.06. Yeah, it would be very close to zero, but it doesn't go to zero. It is some number. It's just very, very, very small. Yeah, but because we're only considering at 1850, so we're not, we're not going to, I guess to zero would make it go to zero. Anyways, no, We're just setting up the formula. Yeah, okay. I don't want to go down that rabbit hole. Okay, so that's what we would have to do for 1850 exactly. So imagine now if we had to find what's the probability that we meet this quota, right? Meet or exceed this quota of 1,850 units. Well, that's going to be 1850 plus 1851 plus 1852. The NPR is slightly different. And we do not use it in this course. It's the number of permutations, which is slightly different. So always just use the NCR. Yeah, just ignore the NPR. Trying to think if we use it. I don't think so. Not in this course. Because it's the number of unique permutations I could have, but no. Okay. Let's see here. Okay. That one's done. How about we're going to check the assumptions for the normal approximation to the binomial. So here we suspect that we have a large enough number of trials to be able to apply that normal approximation, and we'd be right, but we still have to check, right? And so here we need to check that n times p, which is 32,000, times 0.06, 32,000 times 0.06 is 1,920. That is more than 10, right? It feels weird because 10 is it feels like such a low threshold, right? But it's just to make sure that we're not trying to detect some crazy, crazy small probability, right? So this falls apart, even if you have a huge sample size. If you're trying to detect something with a very, 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 very small probability of happening, right, then this condition might not check out still, right? And so that becomes the problem. So then you'd have to increase your sample size even more, right, in order to be able to reasonably detect a success. So it depends on what the P is, what the probability of success is, right? Because here, out of 32,000, we're actually only expecting about 1,920 of those to be O negative, right? So then the number of failures, we could find that two different ways, right? We could find it by just taking 32,000 minus 1,920, right? Or we could do 32,000 times 0.94. I'll do that one, but just convince yourself that either of those would have worked. 32,000 times 0.94 is 30,080, which is definitely more than 10. So that checks out. I'll just show you what I meant. Or 32,000 minus 1,920 is 30,080, right? That's another option you could have done. Just subtracted the expected number of successes, right? And that's relying on the fact that we're expecting, or that we're talking about success failure type of situation. Okay, so it looks like these conditions check out, so we can apply the normal approximation. So therefore, we can apply the normal approximation. Smiley face. Okay, so, oops, crop. let's see here. So now we can answer the question. How likely is Canadian Blood Services to meet its need of at least 1,000? So notice at least 1,850 units of O negative blood. So now, right, if we can use the normal approximation, let's start with putting this into a graphic. Not really a graph, but a graphic. Okay, so we said from the previous part E, I guess, that, okay, we can use the normal approximation. So that means I can draw this curve. I also know the mean was, well, it's going to be 1920, but let me just go back to it. The mean is 1920. And what I'm going to do is I'm going to use 42.4829 as my standard, as my sigma. Okay. And so here I'm going to say, recall mu equals 1920 and sigma is 4829 to 4 decimal places. I just picked 4 decimal places, just kind of out of the blue, but you want to have enough decimal places. So what does that mean? Well, it means that this normal distribution is going to be centered on 1920. Okay. And the observation that I'm interested in, right? So I want to find the probability, how likely, so that's finding a probability, right? And so of at least 1,850 units. And so here we have the number of units of O negative blood on the x-axis. And so here I'm going to put 1850. We'll see when we get there. I don't know the numbers. So here, yep, looks reasonable. So here, right, this is 1850 is below 1920. And the area that I'm interested in is at least this area. So really what I'm looking for is what's this area here. And I managed to cross the line there. How about that? Okay, so we're back to a situation that we know how to deal with, right? And so I can say, okay, well, Z is X minus mu over sigma, right? So we have to calculate the Z. We have to standardize it in order to use the Z table. So the observation that I'm interested in is 1850 minus the mean, which is 1920, divided by 42.4829. So my Z is 1850 minus 1920 divided by 42.4829. You were right on the money. Negative 1.64772178.9. Now the thing is, the Z table can only give us, or we can only use 2 decimal places. So we have to round properly to 2 decimal places. And so Z is going to be negative 1.65, right? To 2 decimal places to match the Z table. Yeah. So Z always has to be rounded to 2 decimal places. Yeah. So then what we're going to find is, and maybe just to keep it on the same page, I'm just going to write up here. I know that feels weird, but I've got a page break here, so I just want to keep it all in the same place here. The probability that Z is less than, and it can be equal to, because the probability at at any equal to is actually 0 on a continuous scale, but Z is less than or equal to 1850. Or you know what? Let's just do it properly. So remember before I was, oh, thank you. I'll still show the table, but that's good. So before, right, I was writing out the blurb using the Z table. We find the area to the left of negative 1.65 is, turns out it's 0.0495 from the chat. And so the area to the right would be 1 minus that, and that's how we arrive at the answer. You could still go through and write that all out. That would be a proper way to answer this problem. What I'm going to do is I'm going to start pushing you towards the probability notation, right? And so the probability that Z is greater than or equal to negative 1.65 is 1 minus the probability that Z is less than negative 1.65. I'm going to bump it over just a little bit, maybe, no. You always want to try to stack your equal signs. Sometimes I'll bump it over if I need more space, but I couldn't do it. I went back and I stacked them. Right, and so we're going to find that the probability to the left of Z equal to negative 1.65 is 0.0495. I'll show you where that came from. Go to the Z table. And not these are from before. So here I'm on the positive side of Z. Sorry, it's just catching up here. So I need to go to the negative side. Negative 1.65. So here I'm going to highlight the negative 1.6, and then I'm going to join it up with 5.0495. Okay. And so 1 minus that is, yeah, exactly 0.9505. So this is where we got this number from, the 0.0495. But remember, these table entries, right? So all those numbers in the body of the table, those are called the table entries. And they're always going to be the area to the left, right? So you have to remember if you want the area to the right. So here, this is going to be 0.9505. So then, therefore, how likely is the Canadian Blood Services to meet its need of at least 1850 units of O negative blood? The probability that they meet their need is 0.9505. Therefore, the probability that they meet their need, I'm all over the place, just trying to keep it on the same page here, of at least 1,850 units is 0.9505 or 95.05%, right? Probabilities are decimal versions, but our brains can handle that conversion, right? The 95.05%. Nice. Okay, so that's how we could use the normal approximation. So now all of a sudden we have a way to calculate these kind of huge probabilities, and it just takes us back to the normal distribution. Okay, so that's the end of the binomial. Now, what I want to do is I want to take us back and introduce some other distributions. Okay, they're going to be less important. Okay, but it's good to have a good handle on, what these are. So the first thing I want to talk about is a Bernoulli trial. And I didn't introduce it, even though we've already talked about it, because it's just one trial where the outcome is either a success or a failure. So notice how a binomial is just a bunch of Bernoulli trials. But for whatever reason, when I was learning it, I found that really confusing, right? So how do I know if it's a Bernoulli, or how do I know if it's a binomial? So for me, I like to introduce the binomial first, and then we can say, well, we could look at the easy case of a Bernoulli trial and know what's going on there. And so let's consider some other distributions. Okay, so a Bernoulli distribution, or a Bernoulli trial is usually what we call it, is just one trial with a success failure outcome, with only two possible outcomes. Success, failure, right? P is still the probability of success, and Q is going to be the probability of failure, but notice that it's just one trial, right? And so what we've seen is the binomial is n Bernoulli trials. So the binomial is n Bernoulli trials. So the Bernoulli is not that important, but we do reference it when we're talking about success failures, right? Then we're talking about a Bernoulli distribution. And to save us some writing, I'm just going to steal it here from the textbook. I was checking earlier, and the textbook used to have links to the videos, but I think they grouped them all. So at the beginning of chapter 4, there's a link to, I think, all the videos. So there are videos for each of the chapters that the authors have put together, and I haven't watched a lot of them, but I mean, it's a nice resource if you're struggling with one of these concepts, right? So just keep that in mind. Okay, so here, if X is a random variable that takes a value 1 with probability of success P and 0 with a probability 1 minus P, then X is a Bernoulli random variable with a mean of P and a standard deviation of P times 1 minus P. Notice that N is just 1, right? So we knew this. If I told you, okay, what happens if N is 1? Well, 1 times P is P, and the square root of NP times 1 minus P is just P times 1 minus P, right? And so notice that N is just 1. So I actually find that it's easier to go from the binomial back to the Bernoulli, because then it doesn't seem so weird, right? The next distribution that I want to talk about is the geometric distribution. Okay, and so the geometric distribution is it's going to be the probability of seeing the is it the first success? Yeah, the first success on the nth trial. Okay. It's the probability of seeing the first success on the nth trial. How is that different from the binomial, for example? Well, now we're looking at what's the probability of seeing the first success on the fourth trial? What's the probability of seeing the first success on the fifth trial, right? And so we understand that if there's some probability of success, then that distribution, the probability is going to get smaller and smaller as we increase the number of trials, right? And so it's a little bit different. And we are assuming that we have identical and independently distributed Bernoulli trials. Okay. So here, we assume we have n identical and independently distributed Bernoulli trials. This identical and independently distributed is shorthand IID. Okay, so I'm going to put that in here, IID, and we use that quite a bit. Okay, and so the identical means that the probability of success is the same for each trial. The probability of success is the same for each trial. Okay. And the independent is that each trial is independent of the previous trial and the next trial, right? And so each trial is independent. Each trial is independent of any other trial. We said that for the binomial as well. So technically in the binomial, we also assume that we have n IID Bernoulli trials. Okay, so note, we assumed we had NIID Bernoulli trials. Oops. Come on. Bernoulli trials in the binomial case. Sometimes it was a stretch. Oh yeah, so here, right, so we assume that we had NIID Bernoulli trials in the binomial case. We didn't call them that, but now I'm introducing this new terminology because I feel like we're ready for it. But in terms of the comment in the chat here, so now if we're talking about the probability of seeing the first success on the nth trial, okay, then what could we do? What we would do is, if you think about, okay, if we have independent observations or independent trials, then we could use the multiplication rule, right? And we could find the probability of this happening is going to be so you have a failure, a failure, a failure, a failure up until the nth trial where you have a success, right? And so for the geometric distribution, we would have a situation with a failure, 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 all up to the nth trial, which is the first success. Right, so the first trial, second trial, third trial, which means that you would have n-1 failures, right? And then the last one is the success, right? And so here we have n-1 failures. So that's how we get to the formula for the geometric distribution. And I'm just going to steal it from here because why not? And so here, right, the textbook does, of course, go through it. If you haven't been reading the textbook, we're going to be following it pretty closely. And so if there's ever anything that you're kind of, not sure of, then it's in here. Okay. So let's bring in this whole kit and caboodle here. So then if the probability of a success in one trial is P and the probability of failure is 1 minus P, that's the same as what we've been dealing with, then the probability of finding the first success, right? And so the first success makes it the geometric. Okay, what's hard is when you read a question, you need to figure out, okay, am I talking about the first success or am I talking about the number of successes in n trials, right? The number of successes would be the binomial. The first success, if I just want the probability of the first success, that's going to be a geometric, right? That's the hard part, is reading these questions and figuring out which one to use. The math here is not bad. So then, like we said earlier, right, you'd have some probability of a failure, 1 minus P. And so that would have to happen n-1 times. So to the power of n-1 times P. So we can find the mean and the standard deviation and the variance here, right? This is the variance, sigma squared is the variance. We're not going to talk about how those came about. We didn't talk about them for the binomial either. We just accepted them as truth, right? If you want more of that, we do that in Stat 240. But you don't want to do that. No, right? We can just accept it as truth in this case, or in this course, I should say. Okay, and so we have a mean and we have some standard deviation, 1 minus P over P squared, weird, and then square rooted, but that's just, we're accepting that as the truth. So here, right, this is how we find the probability, right? The probability of a success on the nth, or the first success on the nth trial. So I'm going to highlight that. The first success. Okay, good. There are a couple more distributions that I want to talk about. The next one I want to talk about is the negative binomial. So we won't have time to do any examples, but I'll see if I can whip something up for tomorrow, I guess it is. But I do want to do some review too, so, or at least give you the lay of the land. Okay, so the next one I want to talk about is the negative binomial. The negative binomial is, yeah, so this will be on it, obviously, because I'm going to focus on the binomial and the normal approximation to the binomial, but it's good to have a, on a multiple, or in a multiple choice situation, can you identify which distribution would apply, right? So I'm not going to get you to do any calculations for this stuff for this test, but I do want you to be able to read a question and identify, okay, is it a negative binomial? Is it geometric? Or the last one I want to talk about is a Poisson. So we're not doing any calculations because we haven't done that, but we do need to have these definitions and have that under control. So it will be on the test, sort of. But for calculations and stuff, I'm going to focus on the binomial and the normal distribution, of course. So the negative binomial is the probability of seeing the kth success. So that's kind of like the geometric. So the probability of observing the kth success on the nth trial. Okay. So it would be something like, what's the probability of the fourth person who came into the fourth donor being O negative out of those 32,000, right? So on the on the nth trial. So it could be on the 100th donor. I'll grab the formula here. But like I said, just be able to identify which is which. Okay, and then the binomial, great, we did that. And there's some notes there. There's some more practice, so that's good if you want it. But the one I want is this one. Okay. This. Oh, come on. So the negative binomial distribution describes the probability of observing the kth success on the nth trials, where all trials are independent. And so the probability of the kth success on the nth trial is, we're going to calculate it in a similar way that we did for the binomial, right? This looks very similar, except we have n-1 and k-1, and then everything else looks the same. Right, and so that's what makes it the negative binomial, but we interpret it in a different way, right? The kth success on the nth trial. Okay. So yeah, what would that be? What's the probability that the 40th donor comes in, or sorry, the 40th O negative person is the 1000th person to come in, right? And then we don't tend to use the negative binomial so much, but one that we do use is the last distribution I want to squeeze in here is the Poisson distribution. Poisson, fun to say, fun to do. And so the Poisson is a pretty important distribution, Poisson distribution, and it is for counts. It's the probability, and I have them written down, the probability, because I don't do these so often. The Poisson distribution is the probability of k occurrences of an event over a specified interval of either time or space. Okay, and so the probability of k occurrences of an event that should say event over a specified interval of time or space. Okay. So what we need, and all we need, is the average number of occurrences in that interval of time or space. So what we mean is you need to know the average number of customers that come into your store per hour, for example, or the average number of potholes in 100 meters of road, right? And so it can be either in time or in space, right? But notice that this is a counting distribution, right? Because we're counting the number of customers or we're counting the number of potholes. And so all we need is the average number of occurrences in the specified interval. Okay, I'm going to grab that calculation because it's actually kind of a fun. Oh, and here they clarify the binomial versus the negative binomial, but I'll leave that for you to read. And just get to the Poisson. Suppose we're watching for events and the number of observed events follows a Poisson distribution with a rate lambda. Okay, so this is a lambda, and that is what we're talking about. So the rate is lambda. I think it's LAMBDA, lambda. Pretty sure there's a B in there. Anyways, lambda. And so the rate, right, that's the average number of occurrences in that specified interval. Okay, and so what we're going to be able to calculate is we could find the probability that you observe K events. So in this, if we think about, if I know that on average I have 4 customers in a store per hour, right, then the probability that I see 5 customers in a store per hour is going to be 4 to the power of 5 times e to the negative 4 divided by k factorial, so 5 factorial, right? And so k can be any countable value, 0, 1, 2, and so on. And so k factorial, it's an excited k. K factorial is k times k minus 1 times k minus 2 times k minus 3, right? And so for 5 factorial, just as a side note here, for example, is 5 times 4 times 3 times 2 times 1, right? And also 0 factorial is 1. Okay. And so it does use the factorial. In fact, the choose function also uses the factorial if you wanted to do that. And a lot of calculators have a little factorial button, but I just use the choose function. Okay, and so let's refer to the examples here. So the Poisson, oh, let it catch up. The Poisson distribution is useful for estimating the number of events, so counts. So having a heart attack, right, in some per year, maybe, getting married, getting struck by lightning, these are all counts, right? And so the Poisson distribution is a counting distribution. The Poisson is a counting distribution. Oops. All right, I'm out of time. But if you have any, yeah, having a heart attack for the test next week, right? In the next week, that's the interval. How many heart attacks do we count? With a rate of 0, hopefully. Yeah, with an average rate of 0, how many heart attacks should I be expecting? All right, so if you have any questions, let me know. Otherwise, I'll see you tomorrow for some test 1 review. All right, and I'll stop this.